In this video, let's look at another feedback, which is the shunt feedback. So the shunt feedback works typically when your feedback network shows up as a shunt connection or a parallel connection at the output and as a parallel connection at the input, right? And this is done typically in a amplifier where the input is the current and the output is a voltage. Remember, when you want to take a shunt feedback, right, at the output, if the output is sampled using a shunt circuit, is normally a voltage sampling, and when the input is fed back as a shunt, it is fed back basically as a KCL, so in which case it's a current feedback. So shunt feedback normally occurs in a trans resistance amplifier, and what happens here is that the feedback network samples a voltage and generates a feedback current that is proportional to this feedback to the output voltage, and that current is then removed from the signal current that is sent into the amplifier. So in a shunt feedback, you sample the output voltage and you modify the input current. So therefore, now when you think about what happens because of feedback, the closed loop gain is going to again drop from the open loop gain, and it's given by A divided by 1 plus A beta, where beta is the feedback factor. Now in this case, again, it's a trans resistance amplifier. The input is a current. So feedback is going to make this input an ideal current sampler, which means that the input resistance reduces from Ri to Ri upon 1 plus A beta, where 1 plus A beta is the loop gain. And similarly, the output is a voltage, and what happens is because of feedback, the output becomes more like an ideal voltage source, which means that the output resistance reduces, leading to an ROF given by Ro divided by 1 plus A beta. Right? So like always, if you want to estimate how the feedback network loads the input circuit, always make sure you're able to break the circuit into this kind of a cartoon, which consists of an open loop path and a feedback path, right? Load is always connected. Now this is an output voltage, so the load is connected across the two ports of the output. The input is a resistance, so normally the signal current is going to have its own signal resistance, shown here as RS, right? Now if I want to estimate what the feedback factor is, again, if you look at the feedback network, you have the input port at 2, the output port of the feedback network as 1. The feedback network samples an output voltage and generates a current. So to find the feedback network, I basically want to find what the short circuit current of this circuit would be. So I apply a voltage at the input of the feedback. I short the output of the feedback network, and I measure the gain between I1 and V2. That is going to be your feedback factor. Remember, the unit of this feedback factor is going to be mho, or 1 by ohm. Similarly, now if I want to find the loading or the impact of loading because of this feedback network, the feedback network, if you look at the output, it is sampling a voltage, right? So the feedback network is taking in a voltage, giving out a current, right? So it is like a transconductance amplifier. So if I want to find what the loading of beta network is at the output, I need to essentially consider the case where I'm applying a voltage at the input of the feedback network, and the output is essentially set to 0, or the output is a short circuit, and I measure the ratio between V2 and I2. The ratio of V2 to I2 is essentially the resistance offered by this feedback network, or the input resistance of the feedback network, which falls across the output nodes of the open loop amplifier. Similarly, now to assess the loading of the feedback network at its output, now its output consists of a current source, right? And so therefore the way we would do to assess the output resistance of the transconductance amplifier would be to create an input which is 0. So in this case, you're shorting the input of the feedback network, or in other words, the input of the feedback network is set to 0, and then you apply a voltage at the output, measure the current flowing in the output, and the ratio V1 upon I1 gives you the loading of the feedback network at the input of the open loop amplifier, and again in this case that resistance is going to fall across the two input ports of the open loop amplifier. And so therefore if you look at the equivalent circuit because of loading is going to look something like this, where this is your open loop amplifier. The loading impact of beta falls as R22, which falls in parallel to RL. Similarly, the loading impact of this, the feedback network, falls as R11 in parallel to RS. Hence the shunt. Both the input and the output look like shunt connections. And so now once you have this circuit, you can estimate the open loop gain of the circuit because of loading. Once the open loop gain of the circuit is known, once the feedback factor is known, you can calculate the closed loop gain, the input resistance, output resistance, etc. So an example of shunt feedback would be something of this sort. So here again, I've given A0 to be the open loop trans resistance, right? Trans resistance means what is the output voltage divided by the input current. So essentially here I have A0, which is an amplifier. IS and RS are the input signals which go into the amplifier. The output is a V, a voltage, which drops across RL. Now where is the feedback? The feedback is occurring, again remember, the way you identify a shunt feedback is that when you have a connection of this sort of a node, right, essentially shows you that currents are being added or subtracted here, which means that the input is a shunt connection. So the input is going to be, the feedback is giving out an output which is a current, right? And in this case the output is a voltage. So RF is the feedback network. It is sampling the voltage V0 and supplying a current at the input of the open loop amplifier. And so therefore the first thing is to calculate beta. So to calculate beta, what do? The feedback network is essentially RF. So beta is given by the current that flows through RF when V0 is applied. So in that case your IF is going to be V0 upon RF, or beta is 1 by RF. And similarly now this RF, it's again a resistance. So similar to the video we had for the series feedback, this is a pure resistance. So this resistance loads itself in the same fashion at the input of the feedback network and at the output of the feedback network, leading to R11 as RF and R22 as also RF. So remember, it's a resistance. A resistance is going to load up in the same way at both its input and output. So essentially now if you think of the equivalent circuit so the circuit simplifies to something of this format, where the RF appears as a shunt resistance at the input and as a shunt at the output. Therefore, my II, or the current flowing through Ri, is given by Rs parallel RF divided by Rs parallel RF plus Ri. This can be simplified into a single resistance of Rs parallel RF. And so the current flowing in Ri is nothing but this resistance divided by the sum of the resistances. Now this II generates a voltage A0 II at the output, and that voltage drops across RL parallel RF and R0. So therefore V0 is given by the voltage that drops across RL parallel RF, and so therefore it's given by this into II. And so therefore my open loop gain can be written in this fashion as V0 upon IS, which is RS parallel RF divided by RS parallel RF plus RI into RF parallel RL divided by RF parallel RL plus R0 into A0. So once again, the open loop gain is known, the feedback factor is known. You can then calculate all the other parameters involved with the closed loop circuit with feedback.